Hello, everyone, and welcome to the third talk of our DevSecOps Talk Series. My name is Juliana. I'm the head of events here at Code Intelligence, and I'll be your moderator for today. First off, just a bit of housekeeping. At the moment, you'll notice the public chat is turned off, but we will open it again at the end of our talk for all of your questions and comments, so please keep them in mind as we go along. However, you can message me at any time via the private chat. So, what is this series all about? DevSecOps is a rapidly growing field that combines the principles of development, security, and operations to ensure that software is developed and deployed in a secure and efficient manner, and so that security is seamlessly integrated into the CI/CD pipeline. This series will bring together experts and practitioners to discuss the latest best practices, tools, and techniques for implementing DevSecOps in organizations of all sizes. Our talk today will be given by Google's Jonathan Metzman, who is a senior software engineer on their open source security team. Jonathan will be exploring how automated security testing is empowering development teams to ensure the safety of open source code. So Jonathan, I will pass it off to you.
Thanks, Juliana. Let me present my tab. Okay. Thanks everyone for attending my talk today. I'm talking about how OSS fuzz can be used to secure third-party packages and mitigate risk from them, both for consumers of open source as well as producers of open source. And OSS fuzz relies a lot on automation, so you'll see how we've incorporated that into this sort of DevSecOps pipeline. First, a little bit about myself, even though I was already introduced. So I've been fuzzing since the early AFL days. I was reading about AFL when it was being blogged about by its author, and I was sort of hooked on fuzzing ever since. I've been working on OSS fuzz for 6 years since then for Google, but I'm only here on behalf of myself today, not my employer. So I assume probably most of you understand what fuzzing is already, but in case anyone wants a refresher, fuzzing is an automated process where randomized inputs are created, either probably through generation and fed to code that we want to target. So at high level, it could be described as having an infinite loop, having something that creates new inputs and then feeds the inputs to the code that we want to test. And the code that we want to test, if it crashes on the randomized input, then we know that an attacker might be able to cause the same sort of issue when that code is in production. And this is how fuzzing reveals security issues. Sometimes I use crashes and bugs interchangeably because typically what we'll do is we'll write bug detectors that when it detects a bug has been triggered, it causes the program to crash. So why use OSS fuzz for open source? I think this sort of background of OSS fuzz kind of led to how it is today. And where it is today, I think, is it's sort of really kind of the best tool for using fuzzing for open source projects. And I think it's the best really just not only for consumers of open source, but also for people that write open source code. The team that OSS fuzz grew out of Chrome. And so Chrome is both a producer of open source and a big consumer of open source code. And so we've done a lot to make it a good process for everyone involved. For example, consumers of open source, by having their code, the code that they're using fuzzed in OSS fuzz, they can cut themselves out as the middleman, and they don't have to say, for example, if you were fuzzing code on your own machine, open source code on your own machine, you would have to sort of triage the crashes and report them upstream. Whereas if your third-party code is being fuzzed in OSS fuzz, that'll go directly to the maintainers. And the maintainers of the open source project will like OSS fuzz too because of the nice automation we provide. We give the open source maintainers things like crash minimization. So trying to reduce the test case to the smallest possible input. So that sort of narrows down what's like the root cause for the maintainers, or things like deduplication. And so automation really has driven it being sort of the driving like philosophy behind OSS Fuzz. We try to automate everything, and I'd say we've done a pretty good job of that. The only things really that aren't automated at this point are writing the fuzz targets and fixing the bugs, and we'll get more into that later. So before I discuss how OSS Fuzz sort of works today, I want to maybe share some future directions that we're going in with OSS Fuzz, and you'll probably see why these directions are sort of a natural fit for OSS Fuzz to go into in the future. Just, I think it'll follow from my explanation of the current state of OSS Fuzz. So at a high level, we fuzz over 1,000 projects in OSS Fuzz, and I think we're probably really like the biggest fuzzing cluster, at least that shares any public details, by probably almost any measure. Like, we fuzz on over 100,000 cores 24/7. We found 50,000 bugs, almost 50,000 bugs over the years. Over 10,000 of those have been security bugs. We fuzz programs written in 8 different programming languages, such as C, C++, Rust, Go, Swift, Java, JavaScript, and Python. And we've been around for 7 years. Now, we, meaning me, I've only been there for 6 of those. But OSS Fuzz, I think, has been around for 7. And so the basic workflow is a developer of an open source project will write fuzzers for their project. They'll commit they'll apply to be accepted into OSS Fuzz, and will accept based on how important the project is. And they'll add a build integration to our repo. And this allows our tooling to produce builds of their project's fuzzers. And so this will be done once a day by our builder, which downloads the latest source code of their project and produces fuzzer builds from that. And those fuzzer builds will be consumed by Cluster Fuzz, which runs the fuzzers, finds bugs, hopefully not, but finds bugs, does a lot of automation magic on those bugs that it finds, and then files an issue with the maintainer. And then eventually it'll check that the issue's been fixed and close the issue once it has. And this is what a build integration looks like. They're really quite simple. On the left, this is for ZSTD, which is a compression library. On the left, you got like a bash script that builds the fuzz targets. And so it's just really calling into the project's build system. And on the right, you have a Docker file, which downloads the project source code and installs any dependencies that the project has. So it doesn't really require any sort of specialized knowledge to integrate with OSS Fuzz. So I mentioned this tool called Cluster Fuzz on a previous slide. And I want to explain what Cluster Fuzz is and how it came to be, because it's really probably like the main core component of OSS Fuzz. So Cluster Fuzz was the fuzzing infrastructure for Chrome. It was meant to find bugs in Chrome and run fuzzers against this big web browser, and it ran on many cores just like OSS Fuzz. And as a result, there were many bugs that were found by Cluster Fuzz. And because of the volume of bugs, any sort of like manual process that was involved in dealing with those bugs really slowed things down a lot, and really like weren't scalable. So for example, if any bugs that were found by OSS Fuzz needed to be manually filed into issues, then that would really not work with like a small team maintaining Cluster Fuzz. So automation really got built into Cluster Fuzz out of necessity. And I think the key automated, or really the most important automated process that ClusterFuzz does is bug deduplication. This is really critical for the sort of continuous fuzzing that ClusterFuzz does. And basically what it is it ensures that the issues we file are unique, that we don't file many issues for the same underlying bug. And this makes this is quite important if you've ever done any fuzzing on your own desktop. If you use the tool like AFL on your desktop, you'll find that it rediscovers the same crash like thousands and thousands of times. And if ClusterFuzz were to file thousands of issues for a single crash, for a single root, for single issue, that would really bother developers, and they would, pretty much ignore us at that point. I think so. Really, crash deduplication has enabled ClusterFuzz to be automated end to end. And I think this is sort of one reason why devs might prefer fuzzing over sort of like static analysis approaches. The deduplication really kind of helps. Another neat automated feature that ClusterFuzz offers is bisection. So it can find the commit range of when a crash was introduced in a program. And this is done with the old builds from the program. ClusterFuzz will take the crashing input or test case and test it on the old builds. And through that, it'll find which build the crash first appeared in. And once you have that build, because we store commit information about each build, you can find a nice sort of commit range for when a crash was introduced. And so after those are done, and a few other automated processes like crash minimization, where we reduce the test case to the input to the smallest possible size to make debugging easier, or reproducibility checking, where we check that the crash is reproducible and let the developer know, so that if they're trying to fix it and it's not deterministically reproducible, that they don't go crazy. We automatically file, or we meaning ClusterFuzz automatically files an issue, and in Chrome actually it assigns the issue to the author of the commit that introduced the bug. And so this workflow worked really well in Chrome, but one day there was a sort of wake-up call in the open source world, and that was from Heartbleed. Heartbleed, as many of you, probably all of you know, really was a devastating bug in OpenSSL that pretty much allowed attackers to leak data from users of OpenSSL. And this bug actually could have been found with fuzzing had someone been fuzzing OpenSSL. The bug was pretty not too difficult but the issue was really devastating because of the sort of widespread nature of OpenSSL. Pretty much like OpenSSL powered the internet at the time. Most websites, I think, used OpenSSL, as did probably most internet users, because I think Chrome and probably Safari even at the time shipped OpenSSL. And so Heartbleed made people realize that, hey, we have this process for securing Chrome. Why not apply it to the open source world to secure the open source packages that we're using? And yeah, I don't have the XKCD toothpick comic because I'm sick of seeing that. And so this is how OSSFuzz was born. OSSFuzz really was just the sort of extension of Chrome's fuzzing as a service tool for open source projects. So we wanted to offer the same workflow to open source developers as we had to Chrome developers. In addition to that workflow, we also tried to offer additional incentives to open source developers so that they could have real reasons to adopt these best practices. Typically in open source projects, there tend to be sort of like underfunded and overworked. And security, although important to many open source developers, is probably not like the number one priority, which typically is making a tool that works, right? So by offering integration rewards, we can get more open source developers to do the best thing for their project. So I like to think of this as kind of paying for the manual parts that we haven't automated. And I'll just go over some of the rewards that we give people. So we pay up to $5,000 for integrating a project in OSS Fuzz, and that'll depend on the importance of the project. So the amount will depend. So something like OpenSSL probably would make like $5,000, whereas most projects tend to make from like $1,000 to $2,000 just for integrating. And then for doing more things to make fuzzing part of your software development lifecycle, like adding in regression tests based on fuzzing test cases, or for making sure that your build system can actually build the fuzzers without OSS Fuzz, we pay up to $15,000. Again, also determined by the importance of the project. And then there's some other cash bonuses for additional improvements. So now I want to talk about some other features in OSS Fuzz and how this leads to AI-generated fuzz targets, which was research that we recently discussed in a blog post. So the first of these is kind of a lie, because FuzzBench is not really a feature in OSS Fuzz. It's actually a different service entirely that is offered to fuzzing researchers to benchmark their fuzzing improvements. But the reason why FuzzBench is important to OSS Fuzz is because of how it lets us keep on top of the latest developments in fuzzing research and incorporate them into OSS Fuzz. So FuzzBench, for example, was showing that AFL++ was doing very well. So we adopted AFL++ in OSS Fuzz as a result. Now, an actual feature that's part of OSS Fuzz is code coverage reports. These will inform developers about which parts of their code are being fuzzed and which parts aren't being fuzzed. And you can imagine how, if your project is partially fuzzed, you can find functions or public, APIs that aren't fuzzed through code coverage reports, and that can inform you about what you should write fuzz targets for. Fuzz targets, I guess I didn't explain, are essentially just like unit tests that sort of take input from the fuzzer and feed it to the code we're trying to test. And we built further on these coverage reports with a tool called Fuzz Introspector that we also offer to all OSS Fuzz projects. And this tool will take the data from code coverage reports and combines it with some static analysis to find out how you can get the most bang for your buck by writing fuzz targets. Fuzz Introspector will tell you which which functions lead to the most amount of code and how much they're already covered. So you can see here that the shallow clone function in tinyxml2 is completely uncovered, but leads to relatively greater amounts of code. So by fuzzing that function, we can get to relatively more code and hopefully relatively more bugs, if any bugs exist, which of course we hope they don't. Now, you could probably see how this leads to using LLMs to generate fuzz targets. Like, if we know which functions to fuzz and we have tools that are good at writing code, why not have LLMs write the fuzz targets instead of involving the developer? And so this is research that we're doing into automate one of the last steps that isn't automated already, writing the fuzzers. So here you can see an example of a fuzzer that was written by an LLM for tinyxml2 based on the introspector data. This works, and these fuzz targets that the LLMs created raised the code coverage percentage of tinyxml2 by 30%. And we found in other cases, like these LLM generated fuzz targets are capable of finding crashes that OSS Fuzz missed. So potentially it has the opportunity to really make OSS Fuzz a lot more efficient at finding bugs by making it rely less on humans to spend their time writing fuzzers. I'll share a little bit about, maybe I'll go, like, one of the ways we do this target generation is by prompting the LLMs with past examples of fuzzers, both from the project and from other projects as well. So now I want to talk about the other direction that OSS Fuzz is going in, which is finding more non-memory safety bugs. So the initial focus in OSS Fuzz's early days was on fuzzing C and C++ code. One reason for this is because, as I mentioned, OSS Fuzz grew out of fuzzing Chrome, and Chrome is a C++ project. So by finding bugs in C++ libraries, we're making Chrome more safe. But people wanted the benefits of fuzzing non-C++ programs as well. But there's a specific reason to fuzz C and C++, which is that those two languages are not memory safe. People can write memory unsafe code, and probably will write memory unsafe code in C and C++. And this can lead to things like remote code execution in pretty much any part of the program. So these bugs are not only like very common in C and C++, but are very important as well. As I said, people wanted the benefits of fuzzing for memory safe languages as well. This is despite the fact that these languages don't have the bugs that we were focused on finding with fuzzing. And so some of these languages, the fuzzing support for them was actually added by Code Intelligence, which added Java fuzzing for us, or really any JVM language, I think. So also Kotlin, I guess, although I don't know if we're fuzzing any Kotlin. And JavaScript as well, more recently. Thank you, Code Intelligence, for that. So the sort of why would you even bother fuzzing these languages, though? The intuitive, sort of obvious first guess reason would be denial of service bugs. Like, if you get these programs to crash, and non-C and C++ programs can obviously crash, then potentially attackers can use those crashes for denial of service. So if we find those vulnerabilities, we can eliminate denial of service attacks or avenues for those attacks. And Code Intelligence's work has led to the discovery of some of these, like in the Spring framework. And OSS Fuzz even found one denial of service vulnerability that could have been used to take down not the entire Ethereum network, but most of the Ethereum cryptocurrency network, since most of the nodes in that network were using Go Ethereum, which OSS Fuzz found a denial of service vulnerability in. But the problem with just looking for denial of service bugs is people tend not to care as much about them. At the end of the day, I think denial of service can always be done with more volume. So finding denial of service bugs can maybe make denial of service harder, but it's probably still possible through other avenues, just greater volume. Even if your web server doesn't have some crazy operation that takes forever to complete because we found this bug, you could just an attacker could just send as many packets as they can at the web server. So we realized that we have to aim higher, and the main reason for this was another sort of devastating bug. That was the log4shell vulnerability in the log4j project. This vulnerability, for those of you who don't know, was a issue in a logging library, log4j, that was used very commonly among Java projects. And this vulnerability was pretty easy to exploit and could potentially have allowed attackers to execute remote code, execute arbitrary code on the victim machines. And so Code Intelligence saw this as an opportunity, hey, could we have found this vulnerability with fuzzing? And so they wrote a bug detector for the log4shell vulnerability, which involved remote JNDI lookups. So they wrote a bug detector for that. Typically that's like not a very widely used feature. And they were able to show that log4j could have been found with this bug detector. Now, it's like one thing to find vulnerabilities that exist, like to write tools that could find them, but it's a much harder thing to write bug detectors for bugs that you don't know are there. So that has been the challenge since then. So Code Intelligence has contributed a lot of sanitizers for JavaScript and Java. These things, these bug detectors or sanitizers, as we call them sometimes in OSS Fuzz, these bug detectors can detect sort of like language-specific issues like prototype pollution, as they found in protobuf.js, but also more generic issues that are not specific to any one language, like SQL injection. My team as well has written some sanitizers for memory safe, for bugs that don't have to do with specifically with C++. We took a little bit of a different approach than Code Intelligence because we decided to look at the syscall level, and this would hopefully allow our bug detectors to be what's the word, like language agnostic, so that you could use them on programs written in any programming language. The main impact of this is that we found a pretty cool shell injection vulnerability in an image parsing library, where by passing a sort of like input into this library, you could get that library to execute arbitrary code, just any shell command you wanted. So that's it for the two directions that we've been taking OSS Fuzz in, and will be in the future. Just to conclude, you should use OSS Fuzz to fuzz your open source projects, because with this open platform, we get these contributions from partners like Code Intelligence and others, and so it's really kind of a sort of center of like innovation, I think, in the fuzzing world, and gets you a lot of the sort of latest and greatest features essentially for free. So yeah, fuzz your code that your open source code that you're using, and fuzz the open source code that you're producing with OSS Fuzz. Thank you very much, and I could take questions now.
Thank you so much, Jonathan. So yes, you can see the public chat is now open. So if anyone has any questions, please pop them in there now.
In the public chat.
Yes. I see. Moment. So I think some have used the private chat. So I see one, why use AI for writing fuzzers instead of creating test cases?
Yeah, we're interested in doing both. I think like the reason why we looked at the sort of fuzzer generation first is because it was sort of the area that had like the greatest potential for improvement. Fuzzers are like already good at finding vulnerabilities. Like they definitely don't find everything, but they're already pretty good at it. And so that part really is kind of like already a little bit taken care of with like existing tools. But writing these tests is something that's really not taken care of at all by any sort of automated means, and that's sort of what we wanted to really work on. Like that, I think that area had the greatest potential for improvement.
All right. I see one more question there. What are some other future directions OSS Fuzz will be going in?
Yeah. So I think one thing that we want to do is use more of like the fuzzbench results, just like more fuzzers that we've seen in fuzzbench in OSS Fuzz. I think like the current process we have in OSS Fuzz might make it like hard to add to test like 10 different new fuzzers on the existing targets that our users have written. So we're going to be looking at maybe changing that, I think, and trying to use more experimental fuzzers. at least for like a period of time. There's another question, right? Like as an OSS consumer, can I see the coverage report of a project or the introspector report? Yeah, I think you can. Oh, I'm not presenting my screen, am I?
Okay. I know, not at that moment.
I meant to, but yeah, like here's an example of, or rather, like this is a list of, it's not like the best UI. It's like a XML page, but there's a sort of directory of coverage reports that you can get for OSS Fuzz projects. And then additionally, we've got this. Actually, this is probably the better link to use. This one will show you links to the coverage reports and introspector reports for projects in OSS Fuzz. And yeah, anyone can access those. Do we consult actual hackers to guide our improvements? Occasionally, it's a good question. I mean, I think, yeah, like obviously some of us have a background in like exploitation. But, you know, obviously like day to day, I work more on like the sort of like infrastructure than exploitation. So I'm not the best person for this, but yeah, we definitely work closely with like different sort of more like offensively minded people within Google to sort of improve our service. Yeah, that's a great question. I mentioned code coverage. Is another question. You mentioned code coverage. What type are we looking at? So this coverage report is from Klang's source-based coverage, and it works on like line. It works on like actual source code expression. So I think in the example I showed, there was like a ternary like if statement, and the branch that was taken when else happened was covered, but like the branch when if was taken when the condition was true wasn't taken. So like even though that was on one line, like it was able to highlight that only one of those was taken, one of those branches. So hopefully that answers the question. I'm not sure. Next question. Does OSS Fuzz also fuzz in less prevalent hardware platforms, e.g. PowerPC? If so, were you able to find bugs dependent on the property of that platform, or for instance, endiness? So we do offer i386 fuzzing, like 32-bit Intel. That's not a very sort of like exotic platform. I really want to do ARM support at some point. There's a few things blocking that, but Google Cloud does have ARM. And so we run pretty much all of our fuzzers on Google Cloud. And so we're kind of like limited, I would say, by what they offer. And like, I'm not even familiar of many other clouds that offer PowerPC. I guess probably like IBM's might, but yeah, we don't do on PowerPC. I think you would find different bugs. I think just like it's interesting, but and I haven't investigated it very well, but I probably should. I think like when you use different sort of like compilation configurations, you end up finding different bugs that probably were there, just happened to be missed by like the sanitizer. So like I've gotten bugs like I actually did one project where I started running all of Chrome's fuzzers, which were initially running on Linux. I started running them on Windows, and the Windows the Windows versions would actually find bugs that were in code that had nothing to do with like OS specific things. Like, but it's still just because of sort of like different build process, like the binary was different in such a way that this bug was revealed only on the Windows version and not on the Linux version. So yeah, it's a great question. And I think just like the lesson of fuzzing is like increase diversity and, will make you find more bugs. So I would, if you can fuzz on more interesting platforms you care about, definitely do it. But I don't think we'll be fuzzing on PowerPC, probably ARM though soon. When to use Jazzer, fuzzer from Google, and OSS fuzzer. Jazzer is actually from Code Intelligence. That's really for Java and JavaScript, whereas tools like libfuzzer are for, I think, pretty much all other languages. Ethereus uses libfuzzer for Python, and I think Go has its own built-in. But yeah, sometimes these different tools are for different programming languages. Which types of bugs did you find, and in which language? Only memory-related / access violations. So I think I kind of like maybe overgeneralized. So the focus was on C++ specific bugs, which aren't really only limited to memory safety. Like there's also undefined behavior types of bugs. And so like we found tons and tons of those as well. In terms of, I suspect the question is more about like the memory safe bug detectors. And yeah, like in some of those, there's definitely been a lot less of those. And I think part of the reason is just that the bugs are less ubiquitous in programming language, in memory safe programs. Like for example, like a program that has a shell injection vulnerability will probably have it at only one place. Whereas like you could have memory safety issues like anywhere in the program pretty much. But so yeah, like we found like denial of service in memory safe code. We found shell injection. We found I think one sort of like SQL injection type things. I don't have more off the top of my head, but I probably could get you some. Antonio, would the goal be to completely automate the fuzz target creation process with LLMs, or use LLMs to increase? Okay, yeah, that's actually a great question, and one that I should have sort of answered when presenting. The end goal would be to start fuzzing projects that aren't fuzzing at all just by using like automated means. So we're starting with the easier problem of fuzzing existing projects and improving that fuzzing. But yeah, I think the end goal, of course, is to go towards just fuzzing to begin with the help of LLMs, using LLMs to start fuzzing a project from scratch and not involving humans in that process. Antonio, is it beneficial to use fuzzing tools that are language specific or language agnostic, or both? It's a good question. I think like I'm not so sure when you even have the option. Like I think like in the early days of AFL, people were using GCJ to compile Java to native code, and like that allowed them to instrument to fuzz Java code with AFL. And now obviously Code Intelligence has Jazzer, which is libfuzzer based. I think like yeah, I think I don't have a great answer for like when's a good time to do one or the other. I know that like I think like Go fuzzing at some point might have been maybe not as mature as libfuzzer. So I think libfuzzer had some there were some advantages to using libfuzzer instead of Go's built-in. But like definitely don't quote me on that. I'm certainly not an expert on Go's fuzzing process, like internal fuzzer, and I think it's actually probably improved. So it's an interesting question, but I don't have a good answer. Okay, I have some questions in private chat. I don't know if I should answer those.
I think those were already asked in the public.
Okay.
Those users were asked in the public chat.
Okay.
So I think that's it. If anyone has any more questions, I think I think you've answered quite a bit. Thank you so much, Jonathan, for your talk and for all of your answerings. And thank you all for viewing. If anyone would like to watch the talk again, we will be sending you all a email with the recording afterwards, so you'll have it for your reference. So thank you, everyone, and until next time, take care.
Yeah, feel free to reach out to me on Twitter, by the way, Metzman J, if you have questions. See you.
Take care.